Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about two-stroke engines progress. So let's dive deep into it. Now, just to give you a rough idea, whenever we are talking about stroke, what the hell does that mean? That simply means travel from one end to another end. Basically, it could be top dead center to bottom dead center to top dead center. Basically, one linear travel motion is one stroke. So if you are going basically complete things that you need to do to get power, in two strokes, we'll call it two stroke. If you need four complete travel to do full combustion event, we call it four stroke. So normally, generally, because it's a linear motion, you do not want a linear motion, you want a rotation for your wheels, for your generator, for your propeller. So we generally connect that puppy to crank. Now crank 99.99% of the time will give you 180 degree of rotation for linear travel, as in from top dead center to bottom dead center, you will move your crank by 180 degree. That is almost fixed. I have not seen any design that generally changes that much. So most of the time you can just count on it. Now there are other stroke counts, so to say. We generally use two stroke and four stroke. Irony is that world started with sort of two stroke, and then we went in very small two strokes, very large two stroke, middle stroke completely disappeared. So middle section of power band is only filled by four stroke. Now there are other mechanism like Porsche is trying to do something very weird where they have a marriage between four stroke and two stroke, making six stroke system. There are other people who are also claiming six stroke system where you have something else going on. For example, you could have water injection into the cylinder to cool down the cylinder and basically expand and vent out. It just adds like a pseudo power stroke. Basically you have one power stroke that gives you, let's say, 1 kilowatt of energy. This steam injection, water injection that becomes steam, that gives you one mild power stroke. So let's say 1 kilowatt, and this will be 300 watts maybe. So those will be six strokes. So there are a lot of people who are trying some weird things, but 99% of the time, if you're putting your hand on something, if it's small, it's a two stroke. If it's a medium size, it's a four stroke. If it's huge, it's two stroke. So these are the primary backbone of our civilization. Now, how would you tell the difference? Very simple. Four stroke has complete breathing. There is no overlap. So basically it breathes. That's intake stroke. Then it compresses. That's the compression. Then kaboom happens. After that, it exhausts. So everything in, when you are talking about a four-stroke engine, is very contained. That's the core benefit of this. Everything is contained. Benefit of that containment is that you have complete control over every single variable. Meaning, what if you want intake to be shallow, right? You do not want engine to breathe completely, especially for low power bands. That may be desirable. So you're like, okay, you have control over your intake valve. You're like, you control it. Like, nah, bro, you don't need too much. What if you want to make sure you do not waste energy in compression? Again, compression stroke is completely independent. You can make sure your intake valve remains open bit longer, so leak out a little bit of compression. That's what we call auto cycle. So you have a lot of option, even in boom stroke and exhaust. How much exhaust do you want? Now, generally, you want to evacuate everything out, but sometimes if you want to do what we call exhaust gas recirculation, you may be like, nope. Like if you need to open it for 5 milliseconds to exhaust all of it, you may only open it for 3.5 milliseconds. It's like, whoa, some amount to be there to have as an inert gas buffer. So you have a lot of control in four-stroke systems. But again, inherently, you have one boom event and a three push event. So one boom, and you have to wait for three travel strokes, so to say, to get power. So fundamentally, energy density is not that great because you have one boom and now you have a flywheel that is coasting everything. So if you have seen old school generators where they had one piston system and you had like massive flywheel, the flywheel was there because they had to compensate for three stroke travels that are not actually doing anything. Now two stroke, how does two stroke work? Two stroke generally has overlap. So it can have a boom event while it's doing the suction event. It could have like a compression. It has overlap. How does it overlap? That depends on the design. So, but again, it's not as clear cut. In four stroke, every step is very clear, very controlled. In two stroke, you have overlaps. So, and generally, simplest way of thinking in this way, like the work is done from the top side of the piston and on the bottom side also. So bottom side is also helping you to breathe. Instead of having an independent stroke that is like breathe, you just have like piston going up that is causing the vacuum in the bottom section that is drawing the air in. So that is the core difference between four stroke and two stroke. Four stroke, every stroke does only one thing. Two stroke, you have overlapping action. You get a little bit of control, but both side of the piston is working. Generally the front and the back, both are working, top or bottom, whatever happens. So If two-stroke exists and we started from that, what was the problem? Well, two-stroke have some good stuff. Primary good stuff is that it has very high power density, because again, you do not have phantom strokes as many as in two-stroke. Two-stroke has like boom, phantom, boom, phantom. Three-stroke, basically normal four-stroke is boom, phantom, 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 boom, phantom, phantom. So you understand, like fundamentally, if your RPM is fixed, you have less amount of boom events happening that is actually giving you power. So if you are designing in the same constraint, you can get 1.5 to 2x power. So a lot of dirt bikes, and specifically, this is the reason why you can have very small two-stroke engine, but not very small four-stroke engine. It's not that you can't build it. It's just that the engine would be this small, but the breathing apparatus and the timing valve and all that, those will become huge. So generally, for power density point of view, you get a lot of oomph, 1.5x to 2x if done correctly. And it has much less phantom draw, as in every component that is working in an engine is taking some energy away, because you have only one energy source, one boom event. So the more phantom load you have, the less efficient the engine will be. So fundamentally, you can design a two-stroke system in such a way that it does not have any valve or only one valve. Or some designs you can have zero valve, and yes, I do mean even without reed valve. There are certain piston window design that allows you to remove the reed valve also. So if you want to design it, you can have a system that just has nothing. It just has one moving part like piston, crank and all that jazz, and the end, there is nothing more than that. So that's why you can make it, if you want to make it, ludicrously power dense. Like even today, like you can make these puppies ludicrously power dense. And the primary reason why we don't use that, if it is that amazing, is simply because it breathes through the intake, specifically the petrol-based systems, gasoline-based system. So whenever you are doing this, basically your piston, when it is going down, it's compressing the air. Cool, awesome. But here's where the heck it's compressing? It's compressing in the crankcase. There lies the core problem. Crankcase is not isolated. Four-stroke allows you to isolate the crankcase. Basically, everything below the piston, or specifically the piston ring, is independent, meaning you can have that puppy submerged in oil in four-stroke. So in four-stroke, you can have this. What is the benefit? This puppy will last forever. Second penalty that you solve is that in two-stroke, because again, this area is getting swept by airs, either you have to use roller bearings, which again, you have to do. Even with that, it will not last very long time. You have to put some amount of fuel and oil in the air that is you are sucking in. Basically, old motorbike, you had to use basically cups to measure how much petrol you are putting in and how much oil you have to mix in. Modern designs, you have an independent oil reservoir that based on how much fuel it's injecting, it adds on its own. But you can understand that this area is not very oil lubricated. That creates a scenario. Given the same metal hardness, so to say, that is utilized here, same metal alloy, this puppy will not last because it does not have the love of oil. So this puppy does not last very long, meaning you can build this. These will be very powerful. But again, unless you are building some sort of dirt bike, which people are not expecting to use for 100,000 kilometers, this puppy will kaput itself very quickly. Like these people who are using this, they're used to the idea of rebuilding the engine, because again, it's not going to last. Inherently, it's not going. It does not have the lubrication advantage. And that itself would not be that big of a deal unless the fact that the oil is also going into combustion chamber. That is a big no-no. So if you dumped a lot of oil, something like this, and it went into combustion chamber, you will not have a combustion. Oil does not burn, even though it's oil. Gasoline burns, diesel burns, oil does not. So oil, you have to have very small amount. Penalty, very poor lubrication. Second penalty, when you do cold start, it does not burn properly. Like you have to have very small amount. It will burn, of course, but you will get that white smoke, classic white smoke. It's not good. So fundamentally, from a lifespan point of view, like let's say you buy this puppy and you're like, okay, I'm going to drive it for decades. Yeah, no. Now, old designs, they had this basically compensation built into it, basically wear and tear built into the design, so they could wear out for years. Only thing would be your mileage will slowly start to degrade. And let's not even talk about emission, because again, catalytic converter, they are very good at NOx, very good at carbon monoxide emissions and all those naughty stuffs. It has no ability to handle oil exhaust. If you basically start to dump direct oil exhaust, it's like, bro, I give up. It just gives up on it. So fundamentally, that's the reason why we do not use it. It has low lifespan, as in like how long this component will last, and oil burn. Penalty, you cannot deal with emission, meaning how clean our air is. And like, no, our air is no, it is very clean. If I replace all car engines with a two-stroke engine, 5 seconds later, you will be like, yep, I want to go back to clean for air. So these are the fundamental problem. And all other issues are minor issue, where it's like, you're using sound pressure backblast to make sure that fuel, air, charge does not leak out. Again, we refined these puppies, made this puppy very efficient, but inherent limitations are the limiting system, especially with gasoline, where you have basically poor lubrication and oil burning. So oil burning meaning bye-bye emission, let alone Euro 5, Euro 6, Euro 7, let alone those things, you won't be able to clear Euro 3. So these are the fundamental problem. That's why you no longer see two-stroke as primary engines for anything prime mover, as in like if you're moving humans around, it's not happening. So we come to the exception to this rule, marine diesel. Now this puppy is the backbone of modern reality, meaning there's a very good chance anything around you or almost all things around you sometime was connected by a boat, big container ship boat. Now how those puppy move? This puppy, marine diesel. Now marine diesel is a two-stroke engine. Now here's the interesting thing. This is one of the most fundamental achievement of human engineering. These puppy regularly, as in if you are buying a modern engine for your modern container ship, they start from 50% thermodynamic efficiency, meaning how much energy there is in the fuel and how much you can extract. It is bonkers. Like the BSFC, that's the value how you calculate how efficient your engine is. If you are getting good, like a good Toyota fine-tuned engine, you are lucky if you're going to get a 220 grams of fuel consumption for 1 unit of electricity, 1 kilowatt hour. If you are getting into good, let's say Cummins engine, and you figure it out, diesel Cummins engine 4-stroke, you'll be lucky to get 180 gram for 1 unit of electricity. Significant reduction. These puppies start at 160 and many of the modern ones are claiming 150. And be mindful, these are internationally verified. So they are very bonkersly efficient. Now look, okay, how the heck they can be almost 20% more efficient in real world, almost 25% more efficient than what you and I have in real world? Well, first, their operating environment is very fixed. They start these puppy up and forget about it. You start, you coast. For how long? A week. Engine does not change. It's like yeet. So those sort of things does help out. And again, if you can do that with yours engine, that will help out also. But we can't. Real life road condition is far more dynamic compared to a giant ship coasting through empty ocean. So that use case itself gives you a big advantage. Second, thermodynamic advantage is surface area to volume ratio, meaning you can easily calculate what is the surface area to volume ratio of your cylinder events, meaning what is the bore size and what is the stroke. You can figure out that cylinder. You can calculate the volume of the cylinder and you can calculate the surface area of the cylinder. You'd be lucky if you have 1 or 1.5 or something, those range you're gonna get. Maybe something like 0.8, something like that in car engines. Truck little bit better, but not that bad. These puppies 0.05, and yes, it scales. Basically, if you keep hearing about the surface area to volume ratio, like if you expand something, the surface area goes by square, but volume goes by cube, meaning it has enough oomph where you can eject enough amount of fuel, heavy fuel oil, and boom that puppy. It just does not have enough surface area to dissipate heat. Now, like, is that a desirable thing? Yes, because you want heat to create pressure, that pressure to push the piston, and you do not want your boom gases to cool it down. How do you make sure it does not cool down very quickly? Have epic surface area to volume ratio, 0.05. Like, you cannot build an engine that can achieve this. Now, how they can achieve it? Well, they are huge. Even that person, I think, is pretty sure either the engine is small or that person is overscaled. The diameter, as in like the stroke, bore is almost 1 meter and stroke 2.5 meter. These are stupidly large engine, and again that allows them to have the thermodynamic efficiency where they boom it and gases have only one vector to do, because other vectors, as in like the surface area, is not enough to leach enough energy away. So it has enough oomph and it has enough expansion where it's like it's almost like how you have a rifle barrel. The longer the barrel, the more oomph you can do, of course to a point, but you can do that. So these puppies are the most efficient puppy. Now there is a penalty. These engines are not designed to breathe on their own. They do not breathe. They are technically not even two-stroke because there is no intake stroke. You have to force intake stroke here. So what we do, either we have turbocharger or supercharger. Older designs has supercharger, newer designs just all switch to turbo. So you have a blower and that blower does the exhaust system. Basically, you have exhaust valve that opens and then blower flushes the air in through inlet ports. Now, why do you want to do this? Is what we call uniflow scavenging, meaning you flush everything out from bottom to top. Everything. Basically, piston goes in, you just like flush everything out. Fresh air comes in, everything flush out. So that's the awesome part. There is no mixture, there is no mess. It's clean. And you have valve there because again, you have combustion event. So valve is handling the combustion event, and then you open it up, everything goes away. Why do you want to have a supercharger? Well, supercharger runs with the crank energy itself, so it is startable. Then people figured out what's the point, we're gonna put turbo anyway, so yeet the basically supercharger and have a compressed air system just starting one cylinder. Once you can even start one cylinder on compressed gas or multiple cylinder depending on how you want to do it, the turbo can start to spool up. Once turbo does up, it's like, bro, I got this. And again, these things are not designed to like tween, they do not do those things. So they start and they spin for weeks, so that is doable. And not to mention, modern systems are exceeding 51% efficient. Some claims are 54% efficient, simply because now they are doing turbo scavenging. As in, turbo is a feedback loop device, meaning the more pressure it puts in, the more boom event happens and the more exhaust pressure is. So you're getting a feedback loop. So why the heck RPM only remains at 80 to 90 hours? Generally, turbo starts to bleed energy. Now, modern systems, they have a motor generator unit. So it basically starts, instead of venting energy, it's just like, okay, let me put load on the shaft. They can extract enough energy to shut down auxiliary generators on the ship. They will, of course, have auxiliary generator because of the regulations and all that jazz, but they can shut it off. It's like, bro, turn it off. Don't consume those fuel. Exhaust energy. So they're very good. And again, they do not burn oil. As you can see, everything happens on the crank system. Basically, these things are oil lubricated, very thick oil lubricated, and everything is completely sealed from the boom section. No oil burning. Very awesome stuff. Backbone of human industry. Very efficient. And unfortunately, you can't put this in anything small. I don't think this is even achievable. 0.05% surface area to volume ratio in anything. Even locomotives are not big enough to have something like that. But this is the fundamental benefit of marine diesel. Only one valve system, one valve, and you have complete uniflow scavenging, very power dense, and again, low RPM means surface area to friction ratio is very low, very efficient, and again, they don't even have gearbox. They directly yeet the propellers. Now, penalty is because the RPM is so low, the pulse would be far apart. So they have a lot of cylinders, sometimes 12 cylinder, sometimes 16 cylinders. So this is the marine diesel, the most awesome use of two-stroke topology with just forced air breathing in. There is no natural aspiration. Although it can be done where instead of having the turbo, you can remove that part, seal the bottom part, have a reed valves and have a port. It can be done. It's just not done because what's the point? Now we come to the modern hype engine, that is a REV Force engine. Driving for engines, made a very amazing video about this. Although all this engine is doing is basically giving you the same topology of two-stroke without the crosshead. In normal marine two-stroke, you have a linear rod. You don't have linear rod in your normal engine. You have a crank. You always do that. But the reason is it's far more compact. You need compact engine for your engines, for your car engines. For ship, size is free, so they can make it as large as. So they did that. Now how they are doing that? Well, they are adding two cheese. Again, you cannot breathe, so you have supercharger. And they have a rotary exhaust valve. I have no idea why they have that. Like genuinely, I'm genuinely confused why the heck they have rotary exhaust valve. And they have ports. Like intake is a port system. And there is no oil burning. That's the good part. Fuel injection, good. Exhaust valve is there. Now, they do not have flow scavenging, which again, they needed a puppet valve to do that. So if you remove the puppet valve, rotary valve does not seal against a boom event. So fundamentally, this is the best design they could have done. So uniflow scavenging is gone. That complete cylinder cleaning is gone. So what can you do? Well, they have a rotary valve. What's the benefit? Well, no benefit. Like the only thing that after going through their website is exhaust gas recirculation, meaning they can choke the exhaust gas flow. Because you have to understand, if you open a port, exhaust honestly on its own wants to go out. Why? Because again, it's higher PSI than ambient. Ambient is 15 PSI and you have at least 200 PSI even after expansion. So it wants to go out on its own. And again, you have some amount of fresh air in charge that will flush everything. What if you do not let it flush everything? So you have a lot of inert gas into the chamber. Benefit of that inert gas in the chamber at low power bands, that is a desirable effect. So you can do that with this system. And driving for answers, he was talking about like, okay, he allows the port injector to work. It's like, throw away the port injector, put the direct injector. Like, why do you need port injector? Like, that's the useless thing. Why you have port injector? And if they're talking about diesel and in their designs, they have something that looks like direct in-cylinder injection, port injection is useless. And they don't have puppet valves in the intake. Puppet valves need basically port injector simply because that allows it to clean. Now, like, okay, why do you need clean your intake valves? Exhaust valves get cleaned simply because there is a hot exhaust. It's cleansing that puppy, hot cleansing. The intake, it does not get that hot, as in like the surface is hot, but the rod side, it's getting clean air. Now, problem with that clean air is generally you put oil from the crankcase. Basically, crankcase has a system which we call crankcase ventilation. We dump it into oil. Now, why don't we vent it outside? You can. You will not meet regulation now. So we have to vent it inside. So it goes through the engine, then it goes through the catalytic converter. Catalytic converter breaks it down. Cool, awesome. But again, that means you have gunk going to the puppet valves that are on the intake. You have to clean it in direct in-cylinder injection. Here you don't have puppet valve, you do not need port injector, like just have direct in-cylinder injection, which again is necessary for diesel anyway, and wait for like, you know, intake port to be covered, throw away the system. And what about exhaust gas recirculation? Many truck engines have that, like exhaust gas is recirculated from something else rather than from the valves itself. So I genuinely have no idea. It's like a rotary valve is there just because it has a rotary valve, like there is no reason for it. And some people who looked into the patent of this, patent is too vague. Now, be mindful about patents. Patents expire in 20 years. Second, patents have to be very specific. Like a rotary valve cannot be patented anymore. It's done. It's been ancient technology. It's been done there. So what they have patented was not patentable. This sort of design existed. So what they have patented, like if people who are looking into it, again, I would suggest to look into a lawyer, but like their patent is the phase shifting, meaning the fact that they can change it, that is the patent, but not the rotary valve in the exhaust. That was already existed. There are already ancient two-stroke engines that had rotary valves. So the only patent is like they can switch it. And again, the only reason why you want to do that in exhaust is simply because exhaust gas recirculation. So, and they are claiming 50% thermodynamic here, which again, I have no idea, do they mean something else? Because again, according to this video itself, the number of BSFC is only 221. That is a Toyota engine. That is nowhere near a giant marine engine that is touching 150G. 150 versus 221, there is a giant gap between those numbers. So I have no idea. The only selling point of this engine is flex fuel, which again, flex fuel is one of those things that sounds great, is just never ever actually great. You don't even want to do it, even if you can do it. Like for example, Abraham tank's jet engine, it can consume any fuel. Yeah, you do not want it to feed on any fuel. So it's one of those things, like Army loves that idea. It's just like, yeah, it's better to have an engine that can handle fuels if you change the fueling system. So it's like if I'm making an engine, let's say I'm working on a CV engine, and you're like, okay, the CV engine is running on petrol. India has a lot of options. So we have petrol, we have ethanol, we have CNG. So we can change the fueling system. So engine hardware does not change, just the fueling injection change. That can be done. In this, they are doing it by like, you know, they're having multiple ports for hydrogen and all that jazz. So that's the only benefit, which again is not really that big of a benefit because most engines are compatible with any fuel as long as you can change the fueling infrastructure. As in like gas injector would be different than a liquid injector. So this is REV Force Engine. Generally, like earlier I thought like, whoa, then I looked into it and like, huh? And then I looked at even better version of this engine that does not have rotary valve. I was like, yeah, rotary valve is just either to get a patent or just like they actually did not think it through. It's like you can do exhaust gas recirculation from some other way. So this is REV Force engine. Now we come to Deltahawk engine, the best engine I have seen in two-stroke for medium-size use case. So two-stroke engine, diesel direct injection, the best fuel. Why? Simply because they are directly focusing on aviation industry. Now you have to understand, aviation industry in America is two classes, commercial and super rich people. Now that super rich people are stupid. They are still using leaded gasoline. Let me be very clear. There is a leaded gasoline still in production and in use. And again, it's not their fault simply because the regulations on FAA is so tight that engines that are like, you know, approved after World War II surplus store, they are still using that engine. It's because that's so like frustrating to get through the FAA approval. That engine's never approved and commercial just moved to jet. So it's like, who cares? So this company, Deltahawk, they started this design, and again their ancient video is I think 12 or 13 years old, and people are complaining. It's like, oh, what happened? Like 5 years later nothing happened, 10 years later nothing happened. It's the FAA approval of that engine took so long. Yes, it is approved right now. So it is two-stroke direct in-cylinder injection diesel, supercharged and turbocharged. Like, okay, why does it have supercharged? Again, engine does not breathe in this sort of design, does not have natural aspiration, so you have to force it. And why they have turbo? Most likely turbo allows it to breathe better once it at high altitude at a bit higher RPM. Most likely it's altitude because it's a direct prop driven, there is no gearbox, so prop is rotating at direct shaft RPM, meaning turbo is mostly there for high altitude compensation. Dry sump oiling system, again nothing fancy, but does allow to improve situation. No valves. That's the benefit part. It has zero valves, only ports. So you have compressed air going here, and then boom event happens. The exhaust opens first, then you have fresh air charge that does the scavenging. Scavenging simply meaning your fresh air charge is washing out everything. In 4-stroke, you don't need that. In 2-stroke, you do need that. So this is what's happening. Basically, compressed air is going there, and they have fuel injector going boom. And ironic part is, even though this is a modern engine, they have zero electronics, which is like, I did not even knew that was possible now. It's like, this has nothing. As in, if this puppy is spinning, you can have a full flat EMP boom event, and this puppy is like, do I have to care? Like, do I have to care or something? And again, the company had a very simple reason. It's like, FAA approval was brutal enough that like, okay, just get the engine approved, don't put electronics. Getting the electronics verified would be like brutal. So they're like, yeah, let's eat that away. So how does this work? They just have a small, almost same inductor, Pintel injector or some simple design which you used to have, that yes, you can have throttle control also. It's not that complicated. It's like old tractor engine. It's not that complicated. So you have zero electronics to run the system, meaning if the propeller is spinning, you can start it from outside also. And they have FAA approval, and they are flying, as in they made models and they are flying, not hundreds, let that be okay, it's not mass production yet, but they took their sweet time and they got it. And you were like, okay, what can we do to make it even better? Well, the easiest thing is yeet the supercharger. That will remove the parasitic loss. So what can we do? Well, nowadays you can pick up a phone, call the OEM suppliers of F1 turbo systems. F1 turbo, not all, but they have what we call turbo energy recovery system, as in thermal energy recovery system. So benefit of that is this puppy can become your starter rather than having a supercharger. Now, power to weight ratio of this engine is not that great. You're like, okay, isn't that necessary to make it great because it's a flight engine? Not really. These are like, we used to fly on like, World War II on much poor power to weight ratio than this. So, and their philosophy is different. You have to understand, when engine is being designed, it's never designed in vacuum. There is a use case. So this is an engine and they're going so hard on basically FAA approval and all that. Engine will be expensive. So how do you make it cheap? Well, you make it easy to service. People will pay for an expensive engine if they can service it, maintain it, basically go through all the qualification, certification very quickly themselves, as in like, maintenance. So every part in this is external, everything, like the water pump, completely external. You can open it into a fuel injector, completely external. A water pump, everything is in external, which again, I can guarantee you, if you give the same topology, you take this out, dump it into Honda's hand or Toyota's hand, it's like, YOLO, let's make it lighter. They can make it ludicrously light and maintain all the same thing. But again, it will not be super simple. Oh, you have water pump failure, remove the water pump from the outside, replace it from there only. That will not happen. Heck, they have cylinder sleeves, because again, they design in such a way that it can be maintained, inspected, and you're like, why do they need cylinder sleeve? They don't. They just have it because for FAA approval. It's like, bro, deal with it. Again, FAA approval is brutal. And again, India, when I'm working with my CV engine, it's not mine, Ron built it. We are also having to deal with RE. RE is India's research organization that is responsible for engines that run on the roads. So I can't talk much about it simply because I have not got their stamp. They could not talk too much about it because they did not have the stamp. Now they have the stamp. So they are talking about it. They are selling it. It's ready to go. So this is a very, very good design. And again, if you are, you can like basically yeet the supercharger, put a motor generator unit in the turbo and solve the starting issue. This would be really awesome. And power to weight ratio, I can guarantee you, like any Tom, Dick and Harry can make it better. Like it has so many bolts, just like so many bolts, but it was designed with a different philosophy. The philosophy is any Tom, Dick and Harry can fix this without electronics. The only electronics you have is electrical starter and electrical alternator, nothing more than that, which again is ancient. I'm like, bro, nowadays you should have like motor generator unit. Heck, my scooty has that. Like my father has a scooty that has that motor generator unit. We don't have like two independent alternator and starter. That era is gone. Like they could have done that, but I'm pretty sure if they tried to do it, the aviation industry would be like, yeah, we need $50 billion and 10,000 years for approval. So Deltahawk, really good two-stroke design, no valve, no fancy stuff, and it makes sense. Supercharger to get it self-starting and basically turbo for high altitude compensation, direct in-cylinder fuel injection. Basically, they can use diesel, and you're like, okay, how would you get diesel? You're not supposed to get diesel, you're supposed to get jet fuel. Jet fuel and diesel combustion properties are similar-ish, both are compression ignition. So this is how they are designed it. I like this design, like it's far more better, and again, ready for sale, there are far more pieces of it and actually flying. They should look at their FAA old videos. It's like, yeah, we are working, we should get it by next year. It's like, lol, that next year took 15 years. So this was a presentation on basically the updates that are happening with two-stroke engines. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.